In this video, we're going to look at Newton's method. We're going to describe the steps to use Newton's method. We're going to explain what an iterative process means, recognize when Newton's method does not work, and apply iterative process to various situations. So we're going to look at a way to approximate zeros or roots of a function. So apart from polynomials of degree 4 or less, most of the time the analytical methods we have learned in the past will not give us roots. If you think about this in pre-calculus 1, and we did the rational roots theorem, and we said P over Q, and these are possible roots, but sometimes we never found the roots. This is a place in which we can now approximate the roots. So where did this come from? If we start with our function, and we look at a point x naught and the output f of x naught. So here's an example of this function. Here's the curve. And we find the tangent line at the point x naught, f of x naught. If that tangent line then crosses, will cross at some point, we're going to call that x sub 1. And then that becomes our new approximation, right? So now we're going to try doing x sub 1, the tangent at x sub 1, and at the point x sub 1, f of x sub 1, and then we're going to do a tangent. And then eventually what should happen, this is called an iterative process, we just keep doing this process over and over again. What should happen is at some point, each time I do this process, that my x values stabilize out to a couple of decimal places. When that happens, then what we end up with is the root or the solution for that equation or for that function. So here's what's happening. We have our first point, our second point, our third point, and etc. And what we're using is we're using the fact that y minus f of x sub n must be equal to f prime of x sub n, x minus x sub n. And this looks a lot like linear approximation. But since I really want to know when we stabilize, so I really want the x sub n plus 1, we are looking for x sub n plus 1, comma 0, which is the x-axis, which is the roots, which is the solution. So y must be 0, and we end up with 0 minus f of x sub n is equal to f prime x sub n plus 1, which is our goal, minus x sub n. Since this is our goal and we solve for it, we're going to get x sub n plus 1 is equal to x sub n minus f of x sub n over f prime of x sub n. So in other words, what's happening is we are chasing the latest and greatest n, so we use the previous, not latest and greatest n, the latest and greatest x. So we use the previous value for x, and we keep going through this process until our x sub n pretty much is stable. It doesn't change when you're out 4 or 5 decimal places. This is an iterative process. We keep taking the previous answer, putting it back into the function or into this equation, and we keep going through it. It's an iterative process. And this process can be time consuming. So this is a process that if you were to do that, you would probably build code for it, or you might put it in a spreadsheet, but you probably wouldn't do this for very long because it's just number crunching, and so it'd be better to get some kind of program to do it rather than doing it by hand. But we're going to do a couple of them by hand just so we get a feel for it. Here is the procedure. We're going to choose an initial approximation as close to the root as possible. So if we're not given our x sub naught, our initial point, we can use the intermediate value theorem, and we know that if f of a is a positive number and f of b is a negative number or vice versa, there must be a 0 in that interval from a to b. So we can use that, and we'll actually, one of the examples, we will do that. The first couple of ones, they're going to give us the x sub naught that they really want us to use. And then we go through this iterative process, provided, of course, our derivative of our original function doesn't equal 0. And then we terminate, we stop doing this as soon as we either do as many as they're asked to do, x sub 1, x sub 2, or whatever, or until I don't have changes 3 or 4 or 5 decimal places out, whatever it is that you are looking for. So for the first 2 examples here, we're asked to use Newton's method to find the x sub 1 and the x sub 2. Now, they give us the x sub naught, but I could have just kind of picked it by choosing 0. 0 is always a good number to choose, and then some other number that you know may not be zero, may not be the same number, like positive, produce a positive or the opposite sign. A and B, both of these examples actually factor, and we don't have to go through the iterative process, but we're going to go through it anyways. So I'm going to need f prime, I'm going to call this x sub n, because I want to use this formula here. And I want to, especially if I have to go through multiple iterations, multiple attempts at going through this process, I'm going to make it as generic as possible so I can just keep plugging that the next number into this formula. And so this is going to be 2x sub n minus 2x sub n. Now we know that x sub n plus 1 is going to be equal to x sub n minus f of x sub n all over f prime of x sub n. So this is going to be x sub n minus, well, I put x sub n back into the original function, and I'm going to get x sub n squared minus 2x sub n minus 3 all over this derivative I just found, which is 2x sub n minus 2, and that should be 2x sub n, and then it's just 2, that should just be 2, not x sub n, so that's just 2. And so minus 2, so let me fix that over here. Now, it's totally okay to stop and use this as is, but if I can clean this up so it gives me a nicer formula that I don't have to keep going through using this one, this one can be a little cumbersome. So I'm going to clean this up algebraically a little bit. So I'm going to write this as, same common denominator here. I'm going to write this as 2x sub n, the quantity squared, minus 2x sub n, and then minus, and all I did was I multiplied the numerator, which is x sub n, by this denominator. Now be careful when you have this negative here, it does need to pull all the way through, which means it'll be minus x sub n, the quantity squared, plus 2x sub n minus 3. It should be a plus 3, so that should be a plus 3, all over 2x sub n minus 2. And you can see the 2x sub n's will cancel. The x sub n squareds will also combine and give me x sub n squared plus 3 over 2x sub n minus 2. Now this is x sub n plus 1. So that is the term that I'm searching for. So I have to always use the previous term in this formula. So I'm going to go ahead and put in my x sub 1 is what I'm searching for. So it'll be my x sub naught, which was 2 squared plus 3 over 2 multiplied by 2 minus 2. I'm going to get 4 plus 3, which is 7. And then I have 4 minus 2, which is 2. So I get 3.5. My x sub 2, I'm now going to use 3.5 squared plus 3 over 2 multiplied by 3.5 minus 2. And I end up with something like 3.05. Now, this is actually not bad. I would do it again. And what I should end up with when I'm totally done is going to be 3 because, again, this one factored. So I'm just going to erase this, and we're going to do the next example. So looking at this next example, again, they give us the x sub naught, but if I didn't, I could always choose 0. I could put an f of 0, which is going to give me negative 2. I can do f of 2, which is going to give me 8 minus 4, which is 8 minus 2, which is a positive 6. So I know there has to be a 0 between those. So I'm going to find f prime of x sub n, which is going to be 3x sub n squared. So then x sub n plus 1 is going to be my f of, no, it is x sub n minus f of x sub n over f prime of x sub n, which is going to be x sub n minus, I'm going to put in x sub n to the original function. I'm going to get x to the third sub n minus 2 all over 3x sub n, the quantity squared on the x. And then again, I'm going to clean this up by combining, and I'm going to get 3x cubed sub n minus, don't forget this negative will pull through. So it'll be minus x sub n cubed plus 2 all over 3x sub n, the quantity squared. So x sub n plus 1 is going to be equal to 2x sub n cubed plus 2 all over 3x sub n, the quantity squared. So x sub 1 is going to be x sub naught. My x sub naught again was 2, so I'm going to put in 2 multiplied by 2, the quantity cubed plus 2 over 3 multiplied by 2, the quantity squared. So I end up with, in the numerator, I'm going to have 2 cubed, which is 8, times 2, which is 16 plus 2. And I'm going to have 18. And then in the denominator, I'm going to get 12. So I have 18 over 12, which is 1.5. Now I'm going to do x sub 2, and I'm going to use 1.5. So I have 2 times 1.5 cubed plus 2 over 3, 1.5 squared. So I'm going to put that in my calculator. 2 times 1.5 cubed, on my cubed button, plus 2. And then that's going to be divided by 3 times 1.5 squared. And I get 1.296. And then I would continue. Again, though, I could have solved either one of these by factoring. Now, let's take a look at this, in which I don't know. I'm not given an x sub naught, and I'm going to use Newton's method to approximate the intersection points of these pairs of curves. So in other words, I have e to the x is equal to x cubed. Well, that's not a function, so I can turn this into a function by writing this as f of x is equal to e to the x minus x cubed. And so then I'm going to find f prime of x sub n. This is going to be e to the x sub n minus 3x sub n quantity squared. And then that will tell me that f, a sub n, not a sub n, x sub n plus 1 is going to be x sub n minus x sub n in the original function, so that'd be e to the x sub n minus x sub n, the quantity cubed, over e to the x sub n minus 3x sub n squared. Same kind of thing, we get a common denominator, so I'm going to have x sub n, e to the x sub n minus 3x sub n cubed minus e to the x sub n. And don't forget to pull that negative through so that it'll become a plus x sub n cubed all over e to the x sub n minus 3 the x sub n squared. Cleaning this up, I'm going to have some cancellation there. It's not going to completely cancel, so I'm going to have x sub n e to the x sub n minus e to the x sub n minus 2 x sub n cubed over e to the x sub n minus 3x to the n sub n squared. Okay, now this one did not, by the way, give me any zeros, right? It didn't give me an x sub naught, so I've got to pick numbers, so I'm going to choose f of 0 into the original function. The original function, again, was x. It was e to the x minus x cubed. So if I put in 0, I'm going to have e to the 0 minus 0, which is 1, and that's positive. Okay, cool. Now let's try 2. F of 2, which is e squared minus 2 cubed. I'm going to get my calculator out, and I have e squared, because I don't know what that is off the top of my head, we have e squared, and I have cats that are thinking that they need something from me, and I'm thinking they don't, so you're just going to have to listen to my cats cry because they're being jerks. This is equal to a negative 0.6109, so we're going to go with the point -61. By the intermediate value theorem, we know there is a 0 between 0 and 2, so let's go ahead and start with x sub naught is equal to 2. Now, I'm going to let you go through this process because it's going to be a little time consuming, and then I can just tell you what the answer should be. So start out with x sub 1, which is going to be 2e squared minus e squared minus 2 times 2 to the third. And then the denominator, we're going to have e squared minus 3e, not e, 3 multiplied by 2 squared. I'm going to get our calculator out, and we're going to go through this process, and I'm going to use that again into the next one. And what you should get with a couple of iterations is you're going to get your x through some iterations of 1.857. Again, I would probably just put this in a program or put this in a spreadsheet. All right, so let's take a look at this next one. Again, we're going to do the same thing. We're going to set these equal to each other. And so we're going to have f of x is equal to the natural log of x minus x cubed plus 2. That's because I set them equal to each other, and I decided to move the x cubed minus 2 to the left-hand side. So then f prime of x is going to be equal to 1 over x minus 3x squared, and I want to use some ends here. And I'm going to go ahead and do the algebraic cleanup again for you, and then we probably should talk about what is a good choice. So let's do the algebraic cleanup first. X sub n plus 1 is going to be x sub n, and it's going to be minus the natural log of x sub n minus x sub n cubed plus 2 over 1 over x sub n minus 3 x sub n, the quantity squared. So I'm going to go ahead and multiply this by x sub n over x sub n to get rid of the fraction to begin with. And so this will be equal to x sub n minus x sub n, the natural log of x sub n, minus x sub n to the 4th power plus 2x sub n, all over 1 minus 3 x sub n to the 3rd power. It's not over that yet. Went wild and crazy there. Okay, and then I'm going to multiply x sub n by that 1 minus, and so I've got x sub n minus 3x to the 4th n, and then this negative will pull through. Don't forget to pull that negative through. Come over here. And so this is going to be minus x sub n, the natural log of x sub n. Let me get rid of this. That was from the previous one. And then it will become plus x sub n to the 4th minus 2x sub n, all over 1 minus 3x sub n, the quantity cubed. And we have some, not cancellations, but we have some combining that will happen. Those will combine. So I have negative x sub n, the natural log of x sub n. And then I have minus 2x sub n to the 4th power, and then minus x sub n, all over 1 minus 3x sub n, the quantity cubed. Now this is x sub n plus 1. Now let's talk about a good choice. Go back over here. I need to put in something here. So if I put in 1, now let's try 1, f of 1. F of 1, the natural log of 1 is 0, so I have 0 minus 1 plus 2. So this is going to be a positive number. Let's choose 2. So I'm going to have the natural log of 2 minus 8 plus 2. I'm going to get my calculator out and see whether or not that is going to give me a negative number. So I have the natural log of 2, and then minus 8 plus 2. Nice, this is a negative number. This is going to be negative, that's going to be positive. So that tells me between 1 and 2, I must have a 0. So I would choose with either 1 or 2. I could choose x sub naught is equal to 1, or I could have choose x sub naught equals 2. Now notice, most of the time I would choose in the right-hand side, but I could have choose the left-hand side, provided, of course, that it's not going to produce 0 here. Now you're going to go through this iterative process, and when you get done, you should get somewhere around 1.345, something like that, as your solution. Again, you put this through iterative process. So Newton's method works pretty good if you have a program, right? Especially when you have large n values, and if it converges. Now, what does it mean to converge? Well, that means that it's going to go to a point or the same x value. There are times in which it doesn't converge, and we'll talk about convergence more in calculus too, but for us, when we just talk about a convergence, is that we would expect it, our x values to settle down at some point. When do you stop? When do you not go anymore? Well, we stop when the differences are small. I'm not going to make you do a bunch of these. I'm not going to say, hey, you have to keep going until the 15th digit doesn't change, but you can do it. The other thing that's a problem with Newton's method is if your derivative of x sub n is 0, right? So if your x sub n is 0, is close to 0 at any step, that this process is going to be so slow that it may not seem to converge if it converges at all. And if that's true, then you would choose other methods to find your roots or the solutions, and that's in different math courses. So that's it for this video. Nice short one compared to some of the other ones we've done. We'll talk about this more in class.